Hello, my name is Enrique, and I'm going to present my work on energy-aware development of neuromorphic implantables. So this is a bit of a literature review on the open challenges for measuring energy consumption of neuromorphic hardware and spiking neural networks. So let's start with a bit of a context. So what are spiking neural networks? So most of you are probably familiar with the artificial neural networks. These are classic neural networks where information is encoded in floating point numbers, and its operations are done as matrix multiplication of floating point numbers. In contrast, spiking neural networks, the information is encoded in binary spikes across time steps. So for every piece of data, you have a time series of binary spikes, so only ones and zeros. These binary spikes are fed into neurons, spiking neurons, which basically every time a neuron receives a spike, it builds up an internal state, and when that internal state overcomes a threshold, the neuron spikes and throws a new spike to the next neuron. And basically what this does, it removes the necessity of floating point operations, and all operations they become floating point additions, which are much more simpler operations that use less energy. So for the gains of spiking neural networks to be able to have good efficient spiking neural networks, we need to run these neural networks in neuromorphic hardware, which is hardware designed to do this kind of operation of like receiving spikes and building a internal state. And basically there is two ways of doing that. One is digital neuromorphic hardware, which basically is like a step behind parallel processing. So it's a lot of parallel processors with collocated memory next to the processor. So basically each processor acts as a neuron or set of neurons with their own memory where they store their threshold. An example is, for example, Intel Loihi. And then we can also have analog neuromorphic hardware, which is an example in the image, which basically this whole analogy of building an internal state can be built with a resistance, a capacitor, and a comparator with a threshold. The difference between these two architectures is that digital neuromorphic hardware is programmable, while analog neuromorphic hardware is not. So you need to know the spiking neural network architecture before building the analog hardware. So this paper is done in the context of the Self Lab, a lab for smart edge devices for healthcare. And in the project we are working in this lab, we are working on building a neuromorphic processor that can detect epilepsy attack by measuring brain signals, and then stimulate the brain to avoid these epilepsy attacks. So the idea is that this neuromorphic processor implanted in the brain would have a spiking neural network that detects the epilepsy attacks. The problem here is that this neuromorphic hardware we want to build would be analog, but it's a very constrained hardware because it needs to be implantable, it needs to be very low power, very long battery. So we need accurate energy estimations early in development, even before we have like hardware designs or hardware access to like a actual hardware prototype. So these, let's say, exploratory studies to figure out in this field what are the metrics available for measuring efficiency of spiking neural networks and neuromorphic hardware, and if these metrics are useful and actionable for spiking neural network developers that need to design a spiking neural network for, in this case, epilepsy attack, but for any other kind of problem. And we also try to identify what are the open avenues or open challenges that could derive into that new metrics, and where we could do research to find out new metrics that can be useful for developers. So given the niche topic, given the how niche this field is right now, we do a methodology of we follow a methodology of basically an ad hoc literature review rather than systematic. So we start with this paper, Neurobench, at the left. This paper is one of the first attempts into, like, let's say, standardizing all of the existing metrics and methods to measure efficiency of spiking neural networks. And from this paper, we do forward and backward snobbing to collect papers that could be related to metrics and defining metrics, or evaluating metrics. Basically, from these 111 papers, we exclude all of those that are not about benchmarking and metrics, because basically we found that a lot of papers, especially those that cite Neurobench, is just because they use Neurobench metrics, not because they are proposing new metrics or extensions, right? So basically we end with a final set of papers that we then share with the team from the Self Lab, which is a multidisciplinary team that includes hardware designers as well as software and SNN developers. And we create a taxonomy and classification of these metrics together with the feedback from these practitioners. Basically, this taxonomy has four attributes, which are accessibility. It's basically how easy it is to compute this metric and to measure this metric. Do we need access to the neuromorphic hardware to measure this metric, or do we need to basically connect some cables to the hardware, or can we derive these metrics from just the software design of the SNN? Fidelity, which is how accurate is the metric or how accurately it reflects energy consumption of the spiking neural network. Actionability, which is how easy it is to make a decision given a metric. So given a number from a metric, is that something that the developer can use to make informed decisions? And then trend-based, which are basically metrics that might not be actionable per se, but they can give a sense of actionability, or they can indicate improvements or degradation if we track the values across the whole development process. In accessible metrics, we find that 8 out of 13 metrics that we found are accessible. So these are, for example, parameters, effective synaptic operations, which would be like the equivalent of flops, or memory accesses. So these are accessible metrics because they can be obtained from the software models. Basically, if I know that a spiking neural network has X amount of neurons, I know that this means that has X amount of parameters. It will have these effective synaptic operations depending on the size of the data, the size of the model. So we don't need the hardware at any point to measure these metrics. That's why they are accessible. Then high fidelity metrics. We find that 5 out of 13 of the metrics found have high fidelity. This means that they reflect energy consumption of the network with like high accuracy, let's say. So an example is energy per inference or power density. And the problem here is that they are obtained from direct measurements of or from a specialized simulation software that is hard to integrate with, let's say, the SNN developer, with the actual like abstract architecture. So yeah, in general, what we find is that these 5 metrics that are high fidelity, they are not accessible, and the same for the 8 accessible metrics before. they don't have high fidelity. Basically, they don't overlap because there is a gap here between the software design of the SNN, the abstract architecture of neurons and data, and the neuromorphic hardware that we don't have access to. Then as actionable metrics, we find that only 2 out of 13 are actionable, which are activation sparsity, which basically means the density of zeros across the network. Basically, this neuromorphic architecture is an event-based architecture, so basically the most zeros you have, the most efficient the network is, because you don't need to do operations with zeros, only with ones. And basically, we consider this actionable because according to the practitioners, as a sparsity less than 60% is not considered good in literature when you are proposing new methods, new SNN architectures. If you have less than 60% of zeros, it's generally not considered a good sparsity. It will be not much more efficient than a normal neural network, basically. And the second actionable metric we found is power density, which is basically power per area for a chip. And this is actionable due to the context in which we are working, which is implantable chips. And basically, according to regulations by the FDA in the US, but also healthcare regulations in Europe, there is a maximum power you can, or there is a maximum power density you can give to an implantable chip to avoid damage or discomfort to the patient. So if your SNN or if your neuromorphic hardware is above that power density, you know it's simply not valid and you need to redesign. Finally, trend-based metrics, we found that they are 5 out of 13. So these are synaptic operations, membrane updates, sparsity, memory accesses, and training time. And this is because they are not actionable per se, because I don't know, if I tell you, oh yeah, this model has 3 million synaptic operations, that doesn't really tell you if that is a lot or not a lot. It doesn't really give a sense of energy. It doesn't give a sense of it is good or bad. But if you know that you have, in one design you have 3 million and in the next design you have 4 million, then you know that this will probably mean an increase on energy consumption because you have more synaptic operations, even if you don't know exactly how synaptic operations and energy correlate. So this table is basically a summary of all the metrics we presented. As you can see in the first column, accessibility, and the second, high fidelity, we see this gap between the accessible metrics that are not accurate about energy consumption. And yeah, basically from this review and from this table, we identify 2 main challenges. One is bridging this accessibility and fidelity. Basically, it would be really useful for SNN developers to have accurate energy estimates before having to go into the late phases of the project. So having high and accurate energy estimates basically before designing or during the design of the architecture, since it's much easier to basically iterate over different software designs rather than hardware designs. And we also need more actionable metrics in this field, because right now only 2 of them give actionable feedback to developers, and it's just from context of the problem, right? So we need to design new metrics and new approaches that give actionable metrics and make decision making easy for developers. For the first, so we are now going to suggest different research avenues for these challenges. For the first one, for bridging accessibility and fidelity, we suggest a potential research avenue could be creating energy estimation methods based on accessible metrics. So basically, by bridging together the experience from the hardware designer and from the software or the SNN developers, we can create estimates on how much would an SNN how much energy would an SNN take based on the accessible metrics. Basically, we can ask the hardware developer to give some benchmark numbers on how expensive a synaptic operation is, how expensive a memory access is, and create a sort of mathematical models that combines the accessible metrics with these benchmarks and with these, let's say, individual costs of each operation. And for this, we would also need to consider all components of the implantable, because in this study we only focus on the SNN part, but normally for implantables you also have other components like the analog digital converter that is used for reading like brainwaves and converting them to digital numbers. And components like this can be orders of magnitude more expensive than the SNN, which means that it might not be there might not be too much gains if we have like very expensive components. And then for the lack of actionable metrics, we have multiple research avenues. First is working more with trend-based metrics. As we saw, the trend-based metrics can give a good insight when iterating over different possible designs. So one suggestion would be to aggregate this into a more digestible way and that can be more actionable. So for example, drawing inspiration from sustainable software engineering field, we have speed up, green up, and power up, which are basically ratios between different versions of the model, and they are defined as a division where if the number is higher than 1, you are doing worse, then the number is lower than 1, you are doing better. Then another actionable metrics could be ones that that mark large changes in power usage. This is especially relevant for our context because implantable power delivery is limited, as we said before. So we could build metrics, or we could take metrics that basically reflect these changes in power delivery again with numbers that are easy to interpret by a developer. And basically we want to prioritize metrics here that focus on power usage and inference time, because longer inference times means also longer work. The chips is working longer and it's generating more heat, which is more less uncomfortable or damaging to the patient. So some examples of this metric would be power up from before, but also the energy delay product, which combines power or combines energy with time to basically compare like inference times with power usage. A third relevant direction here is battery-related metrics, because in implantable, long battery life is essential. Basically, the battery is implanted together with the chip, and it needs a brain invasive surgery to replace this battery. So basically, as a rule of thumb, in general, a brain implantable battery should last 10 years at least to avoid frequent brain surgery. So basically we could create metrics that and benchmarks that reflect battery life of the model and how the model architecture affects battery life of the device. So this could be, for example, expected battery life or inferences per battery cycle to basically give a sense of how long is this model going to last, how expensive is this model, is this spiking neural network model going to be on the chip battery. And finally, another research avenue would be energy accuracy trade-off, which would basically reflect, when trying to maximize accuracy, basically how much energy does an additional percent in accuracy cost. And basically, is it worth increasing the accuracy on like 0.05% if it's going to cost me 2 times the energy? So yeah, basically these improvements might be negligible if the cost is too large, and it might be better to just keep a slightly lower accuracy in exchange for a much better energy efficiency. So basically the idea of this research direction would be to try and define metrics that can reflect these energy accuracy trade-offs between different versions of the model. As a conclusion for this paper, what we did was classifying existing metrics in literature for neuromorphic computing according to their properties. We identified two main open problems in benchmark and measurements, and we proposed 5 research avenues to improve this energy benchmarking, including like avenues to improve accessibility and fidelity, and avenues to improve actionability of the metrics.